I'm going to discuss the relation between antiderivatives, derivatives, and area. Now, it might not seem like there's any relation between antiderivatives, derivatives, and area, but there is. In fact, the discovery of this subtle relationship is one of the greatest advancements in human history. All right? It literally changed the world. Now, before we continue talking about that relationship, let me show you a simple word problem that pertains to this topic. All right? A boy on a bicycle 10 miles from his house starts moving away from his house at 3 miles per hour. How far from his house is the boy after 5 hours? All right. Pause the video. This is important. Pause the video and try to solve this simple word problem. Make sure you understand how to solve it. Okay, this is going to be key. All right, so I will go ahead and solve it. So I'm going to use calculus language. So we know that, or you might know that the distance from the house as a function of time can be given by this formula. Okay, so at time equal to 0, he's 10 miles away from his house, and after 5 hours, he's going to be 25 miles away from his house. All right, now why did I know that this equation is the equation for x as a function of time, where x is the distance from the house? Well, we know that the velocity is the derivative of this x function, and we know that the velocity is the slope of the corresponding line, the graph of x. Okay, and so therefore I was able to construct this linear equation. And 10 is the vertical intercept. Okay, so that's all well and good. Now let me make some plots. I want to plot x as a function of time and the velocity as a function of time. So we'll have x in units of miles, t in units of hours, all right, so let's see. So the x started out at 10, and it ended up after 5 hours at 25. The velocity, the derivative, was 3 for the whole 5 hours. Okay, so x is a function of time. The graph is, for the 5 hours, is the following line segment. Okay, and the velocity graph as a function, with respect to time, is the following horizontal line segment. All right. Now, let me show you something interesting. Okay? If you wanted to know the distance that the boy traveled in the 5 hours, you could calculate the difference in the distance from the house from the final time to from the initial to the between the initial and the final time. So the boy went 15 miles in those 5 hours. How do I know? Because he ended up 25 miles away and he started out 10 miles away. So this difference in x, delta x, is equal to 15 miles. Okay? Now let me show you another way you could have calculated the distance traveled, which may or may not be obvious to you. You could also calculate the area underneath the velocity graph for those 5 hours. The area, what kind of a shape do we have here? Well, I hope you would agree that the area underneath this horizontal line segment, the shape underneath the horizontal line segment is a rectangle. The area of a rectangle is length times width. So we get 15. All right, so can you see, are you starting to see that there's a relation between calculus, between derivatives, at least for right now, and area? Okay, let me show you how antiderivatives come into the picture. All right, so the velocity is the derivative of, or let's say it this way, v of t is the derivative of x of t with respect to time. All right? Think about the definition of velocity and convince yourself that that's true if it's not clear yet. Okay? Now here's the part that might not have been obvious to you. X of t is an antiderivative of v of t with respect to time. So this is how we're bringing antiderivatives into the picture. Okay? So apparently you can use areas underneath derivative function graphs to find changes in the heights of functions. In other words, we can find the change in the height of the left graph by finding the area with respect to the right graph. All right? I hope that's clear. Pause the video and think about that for a moment if any of that wasn't clear. Now, we could also do the reverse. We could find the area underneath the right graph by finding the change in height with respect to the left graph. Think about what we're doing in that situation. We are calculating an area by analyzing the properties of the antiderivative of the corresponding function. Okay, why? Because remember, x is the antiderivative of v. Okay, so apparently there you have choices. If you want to calculate the change in a function, you can do an area calculation. Likewise, if you want to calculate an area, you can do a change in function calculation. Okay, there's these two problems and they're both related. They both give the same answer. This subtle discovery, this relationship is huge. Okay, we're going to be able shortly to calculate very complicated areas by analyzing antiderivatives. All right? It's going to seem like magic. Okay? So, now it doesn't look very impressive to calculate the area of a rectangle with antiderivatives, but let me show you where we're headed towards. Okay? So, keep in mind, yes, we can use this antiderivative analysis to calculate the area of a rectangle, but let me show you how that could be useful for more complicated areas. Okay, I'm going to erase the board. Suppose we had a function that we wanted to calculate the area under its graph for a certain portion of the graph. So let me draw a coordinate axes. Let me draw coordinate axes. All right, and let's say we had some complex function that was doing all kinds of stuff, and let's say we wanted the area underneath a piece of it, okay, such as between these purple vertical lines. Okay, now if we were content with an approximation to the area, we could approximate the area underneath the red graph between the purple vertical lines as follows. We could find rectangles that fit pretty nicely, right, on the parabola. And let's get really narrow rectangles, and we'll put them right next to each other. Okay, so I have, what, 5 green rectangles, and they approximately, they almost cover all of the area that I was interested in. Okay, if I could find the areas of these rectangles, that would give me an approximation to the area underneath the red graph I'm interested in, right? Now, what if I wanted a more accurate approximation? Well, I could use more rectangles. I could use narrower rectangles, right? I could adjust the height so that it was would give a better approximation. But I could do this process and get as accurate of an area approximation as I wanted to, right? And furthermore, for each of those rectangles, we would be able to use our antiderivative trick, because we know that at least for a rectangle, the antiderivative trick works. All right? So that's the start of that's the start of my explanation of how we're going to use antiderivatives to calculate complicated areas. All right? There's more to follow.